Our talk this evening is the future of sustainable cooling in buildings. Our speaker is Dr. Jesus Lizana, who is an associate professor in engineering science at the University of Oxford and leads research on zero carbon space heating and cooling at Zero Institute. He's engaged in many research initiatives and is a consultant on many building energy related projects across the world, including providing strategic advice to many international institutions. And I'll now hand over to Dr. Lizana.
Thank you very much, Brian. Can you hear me well?
Yep, can hear you fine.
Fantastic. Yes, well, thank you for the invitation. I am an associate professor in engineering science in the University of Oxford. I started in January as a leader of the zero carbon space heating and cooling research at the Zero Institute at Oxford, where we are working together with local partners and international institutions to try to accelerate the transition to net zero. But I started in Oxford 3 years ago as a member researcher of the Future Cooling Program, where our interdisciplinary team were working together to shape and to understand and shape the future of cooling. And my presentation here will be part of the work that we were doing during this time. But first, I would like to start talking about where I come from. I am from Seville in southern Spain, a beautiful city known for its amazing food and a fantastic weather. A fantastic weather, but with last summers reaching temperatures higher than 45 degrees Celsius, something that we never saw before. And this is really creating an issue in Spain, but not only in Spain, even in Oxford. You remember last summers, we saw for the first time in Oxford temperatures higher than 40 degrees Celsius. Not only in Oxford, but throughout the whole UK. We are starting to see the temperatures higher, temperatures that we never saw, and temperatures which one we may need to deal in the future. So it's clear that climate change is happening faster than expected. To address this problem, we were working at different action scales to try to understand and mitigate climate change, to try to understand and reduce the problem of the urban overheating, to mitigate the problem that we are having specifically here in the UK of building overheating, and of course to address people discomfort more efficiently, decreasing energy demand for cooling. A work that we lead locally and internationally, collaboration with more than 40 organizations and institutions globally. And in this presentation, I will focus on two main points, the impact of rising temperatures, and I will talk a little bit about the impact in the UK specifically. And also, I would like to show the right steps to sustainable cooling. What can we do in the building industry, in building services in engineering to address sustainable cooling in the future? And I will start with the first part, with the impact of rising temperatures. Currently, most of the cooling needs and cooling demand are located in the tropics, where half of the global population lives. A common indicator that we use to quantify these cooling needs or heat exposure is cooling degree days. It's the indicator that you can see in this map. This is an annual indicator based on the difference between the daily average temperature and a reference temperature, often set at 18 degrees Celsius. So, for example, if we have a day with a daily average temperature of 20 degrees Celsius, for that day, we will have 2 cooling degree days. And basically, with these indicators, what we do is we sum all these cooling degree days per day throughout the year. Climate change is increasing this cooling demand globally, and is expected to be more than triple by 2050, according to the International Energy Agency, with heat events occurring more often and longer. This is affecting seriously people, infrastructure, the environment, and the economy. It's increasing mortality and morbidity and mortality. Even there is a recent report from Europe showing how 90% of all climate-related fatalities in Europe are related to extreme heat. Even according to the International Energy Agency, it is projected that 10 new air conditioning units will be sold every second from here to 2050, increasing the energy demand for cooling drastically and adding additional pressure to power grids. Of course, this is going to increase the demand for fossil fuel. And at the same time, in the economy, the rising temperatures are also affecting the productivity is starting to affect seriously strategic sectors such as tourism and agriculture. In Europe, a recent report highlighted how heat-related economic losses are right now close to 14% and increasing annually. We might assume that extreme temperatures are the only issue here, and they may not occur frequently in the UK. But let me ask you this question. What is worse, 30 degrees Celsius or 40 degrees Celsius? Which temperature is likely to have a more severe impact on people, infrastructure, environment, or economy? And yes, this is a trick question, but it's a question that for me is really important you to understand for explaining the next point. And I will answer the question later. A good example to understand the right answer to this question is the definition of a heat wave. We call a heat wave as 3 consecutive days with maximum temperatures meeting or exceeding a heat wave temperature threshold that normally is close to the 95th percentile of the daily maximum temperatures historically. Let's compare two different regions, the UK and Spain, where I come from. Something interesting is that in the UK, a day with a maximum temperature of 30 degrees Celsius is a heat wave. This will be a very extreme situation, generating and creating a lot of impact. However, in Spain, in Seville, where I come from, close to this area here, we can see how not only 40 degrees Celsius, a day with an extreme temperature of 40 degrees Celsius is a normal day. It's not a problem. And this is the most important here to understand. Why these strong differences? The main reason is the embodied capital to deal with heat, the physical and sociocultural capital. The understanding of the embodied capital in our built environment is crucial to quantify the implications of heat. And here you see two pictures, for example, in the street where I live, in Seville, one city, one Conwy, one city in North Wales, in a summer day. And this was the main driver that leads us to our recent publication in Nature Sustainability. It is not about the maximum temperatures, it is about the relative change. And here in this article, we wanted to identify and quantify what countries will be highly affected by the absolute, but also by the relative change in heat, in temperatures. So here in this article, we answered the following questions. If the global mean temperature rise increases from 1.5 degrees Celsius to 2 degrees Celsius, what countries will experience the most dramatic increase in heat exposure and cooling requirements worldwide, in absolute and in relative values? This figure shows the absolute change in cooling degrees, this indicator that I was introducing previously. In this case, from the scenario between 1.5 degrees Celsius and 2 degrees Celsius of global mean temperature rise. In the table in the right, we ranks the top 10 regions with the highest absolute changes in this indicator, in cooling degree days. Here we find something that we already know, that in the tropics, we have the countries that will suffer the highest absolute increase in heat exposure and cooling needs globally. Specifically, the top 10 countries more affected are in Central Africa, which will add additional pressure to the socioeconomic development of these regions. So all these regions in the tropics, they are already having the highest cooling needs globally, but they will suffer also the highest absolute increase in temperatures. However, if we analyze the relative change in a similar way, we see a completely different picture. The countries at northern latitudes will face the greatest relative increase in uncomfortable hot days. Here, what is important to highlight is that even though these regions will have a moderate increase in temperatures, the impact of the extra heat will be huge, will be much higher than in comparison with other regions in the south. It's interesting also to see in the table how 8 of the top 10 countries are in Europe, and with the top 10 countries being Switzerland, the United Kingdom, and Norway, with a relative change in this indicator of 30%. Why is the relative increase important? Buildings in other regions are designed to keep the heat inside by maximizing the solar gains and minimizing ventilation, because basically what we want to do is to reduce the heating needs in winter. The problem is that in summer, we have to do the opposite. So here, even with a moderate increase in temperatures, this impact, the impact of the extra heat will be felt more acutely. It's important to recognize that heat is not just a concern for southern regions. Adaptation interventions, adaptation measures are needed globally to prepare for a hotter world. But how can we avoid this problem, not overheating in the north and in the south? How can we address sustainable cooling in the UK? And this will be the second part of the presentation. Let's imagine the situation, which can be a home in the UK or a home in a country, a North European country, in which we have high solar gains with dark surfaces and no solar protection in windows. We may have windows opening outwards, so we cannot install in any window shutters. We have building lofts that are not ventilated, increasing the overheating. And even we may have homes that are not well insulated. It's quite easy to see that with these conditions, we may have outside 26 degrees Celsius, but suddenly inside the temperature is much higher, even higher than 30 degrees Celsius. And this can be perfectly a normal day, a normal summer day in my office here in Oxford, where outside the temperature is not that high, but inside the overheating is increasing drastically. What can we do here to address sustainable cooling and reduce this indoor overheating? First, we need to understand the real meaning of cooling. What is cooling? Cooling is not only an air conditioner. A wide portfolio of solutions for cooling is already available to address cooling efficiently. We need to consider that the adaptation of the built environment to warmer temperatures requires the development of the best available technologies and techniques for cooling. And these cooling solutions can be classified using these 5 key concepts. Solutions for solar protection to reduce solar heat gains, for example, cool surfaces, green surfaces, or shading for openings, or adding external vegetation. Solutions for heat preventions involves mitigating or avoiding external and internal heat gains through the building. External heat gains arise from the ambient temperature transferring heat through the building envelope. The internal heat gains can be due to human activities, appliances, or lighting coming from inside the building. Heat modulation here consists of using the building thermal mass of the building to store heat gains and release them at optimal times. For example, using free cooling at night or natural ventilation at night. Heat dissipation is based on heat rejection from the building through passive or low energy techniques with the support of environmental heat sink at a lower temperature, which can be ambient air, water, ground, or the sky. And finally, the last category will be heat removal, in which we find all the technologies that usually require a high energy input to absorb and reject heat from the indoor space to outside, without necessarily having a heat sink. Despite this extensive portfolio, the main problem is that the easiest and the fastest response to address cooling still lies with the installation of an air conditioner, commonly regarded as the sole technological solution to address cooling. With all these options, what are the right steps to address sustainable cooling? How can we do it efficiently in an optimal way? Well, our recommended steps are 8. Implemented following the right order, they can increase the heat resiliency of the built environment. They can downsize cooling systems and cooling needs. And finally, they can decrease resource consumption and mitigate environmental impact of cooling. Of course, these steps should be implemented considering current and future climate conditions, and of course, considering heating and cooling as a whole in the building design. We don't want to increase the energy demand for heating in winter, and this is quite important. It's something that we need to consider carefully in the UK. Let's start with the first 4 options, the first 4 steps. These steps are related to solutions that I was introducing previously, solutions for solar protection, heat dissipation, heat modulation, and heat prevention. Solutions that we normally call as passive cooling techniques. And these solutions are not new, are well known in the building industry. For example, for solar protection to mitigate solar heat gains, in opaque surfaces, we can implement ventilated and reflected roofs or ventilated and reflective walls. And in the openings in the building envelope, we have a large portfolio of shading devices that we can integrate in buildings according to the building orientation to reduce the amount of solar heat gains. The same for heat dissipation. In this case, for example, for natural ventilation, we can promote natural ventilation driven by wind, by solar, or by the stack effect. And we can find really powerful solutions, for example, cross ventilation or using ventilation chimneys. We can increase the air changes rate in the building largely. And these solutions are not new, of course. We can find even this solution in the ancient architecture of our cities. This is one example of the white villages in Spain, a very popular route where you will find villages, completely white villages with very narrow street to protect the buildings from the sun, or even the famous wind catchers from Iran, the ancient Persian way to keep cool, by capturing prevailing cool winds and directing them into the building to provide natural cooling. If we address these 4 steps efficiently, we have a great chance of eliminating the need for air conditioning. But even if not, we still have different alternatives that we can integrate to reduce even more the cooling needs and downsize the cooling systems. Here, the 5th step consists of using more thermal comfort variables to create comfort. And the 6th step in recognizing the individual real cooling needs through an occupant-centric technology or design. First, we need to realize that thermal comfort is not only about temperature. The temperature value that we commonly see in a thermostat is the dry bulb temperature. But this is not the only indicator telling us that we are in thermal comfort. We have 4 environmental variables and 2 personal factors affecting thermal comfort. The 4 environmental variables are humidity, the air speed, the air temperature or dry bulb temperature, and the radiant mean temperature. And the 2 personal factors are the metabolic rate and the clothing insulation. The opportunity that we have here is that using more thermal comfort parameters, for example, a higher air speed or a lower radiant mean temperature, we can modify the temperature range of the comfort zone in which people feel comfortable. And this is very interesting for cooling. Here, we need to move from the classical approach where we control cooling, you'll see, where we control cooling only using dry bulb temperature. And we need to move from here to a hybrid approach where we can create a comfort environment even at 27 degrees Celsius, but only by increasing the air speed. And this is something that we can do without sacrificing comfort. The next step is about to remember something important, very important. We need to cool people, not just buildings. Because most of the time we are cooling people more than needed or even cooling empty spaces in buildings. And now even more with this hybrid working environment that we created after COVID, where we frequently work from home. The concept here is to reduce the centralized comfort criteria. For example, increasing the set point temperature from 24 to 27 and provide an alternative to the occupants implementing adapted environments with personal cooling. This can help even more to downsize centralized cooling systems, reducing the peak cooling load and decreasing the investment and operating costs for cooling. The target here is to shift from a building-centric design to an occupant-centric design. And we can see even now in the market, there is a growing trend in the market with more and more cooling devices designed to create these personalized environmental control systems. Even the ASRA standard already included in the last update of the handbook fundamentals, this huge opportunity that we have for cooling by using more thermal comfort variables and introducing these personalized environmental control systems. And this is the most important point I would like to highlight in this presentation. Only by modifying the set point temperature by 1 degree Celsius, we can reduce the energy consumption between 5 and 10%, which is huge. Here, what we are suggesting is to move, as I said, from this classical approach that reduce comfort to one single variable, for example, 24 degrees Celsius, in this conventional approach here, to a hybrid approach where we can start using more thermal comfort variables, for example, introducing ceiling fans to increase the air speed, or creating these personalized environmental control systems. Integrating these strategies, we can easily increase the thermostat, the temperature of our built environment without sacrificing comforts and reducing the energy demand for cooling hugely. And this is one example of the BCA Academy Zero Carbon Energy Building in Singapore, where we can start seeing these strategies implemented in the building industry. We can see how we have these ceiling fans in order to increase the air speed in the built environment. And at the same time, we can find these personalized environmental control systems where we can adjust our surrounding comfort environment to the right conditions for us, even for the individual right conditions. If after these 6 steps, we still have cooling needs, we have 2 last steps that will help us to mitigate resource consumption and environmental impact for cooling. They are related to the focus on life cycle and the increase of renewable energy. With the focus of life cycle, what we want to make sure is that we integrate a super efficient equipment in real operating conditions with high durability, adequate maintenance, and the most important, using ultra-low global warming potential refrigerants. Here, the environmental considerations of cooling should go beyond the standard operational phase of cooling technologies, and specifically on the use of the refrigerants or F-gases, the fluorinated gases. F-gases can leak from the units and quickly exacerbate global warming up to 40,000 times more than CO2 in the short term. F-gases used in air conditioning are responsible right now for more than 1% of the global greenhouse gas emissions over the last 20 years. And they are projected to be between 9 and 19% by 2050 if emissions continue business as usual. What alternative can we implement here? Well, the alternative here will be the use of these low global warming potential refrigerants. For example, ammonia, carbon dioxide, or propane. And finally, we need to maximize the use of renewable energy for cooling. And here, thermal energy storage and energy flexibility can play a critical and very important role. And this is super interesting in the case of cooling, since cooling flexibility can benefit from two important aspects. First, it's not the same to operate the air conditioner at daytime at 40 degrees Celsius that at nighttime, when maybe we have 20 or 25 degrees Celsius. If we operate the system in better operating conditions, for example, at night with lower outdoor temperatures, we can increase the seasonal efficiency by more than 25%. At the same time that we have this higher efficiency, this is something that we can combine when we have a higher availability of renewable energy, and of course, something that will be associated to a much lower electricity tariff. When we combine all these things together, we can have a reduction in the operating cost by more than 50%. And this is here, you can see here one example of this conventional operating mode of consuming energy from the grid as soon as we need cooling. And on the other side, implementing these energy flexibility strategies for cooling, increasing the seasonal efficiency of the heat of the system at the same time that we consume more renewable energy and pay less for this electricity. This will be the end of this presentation, but what are the key messages that I would like you to keep after this presentation? The first one is to remember, it is not about the absolute or the maximum temperature. The relative change is critical, and here the UK is not prepared. In summer, it's really important, ventilate first and insulate later. Otherwise, overheating will increase. This is one of the major problems that we have in the UK. We are starting to insulate to reduce the energy demand for heating in winter. However, when we insulate and we don't modify the solar heat gains and we don't address properly ventilation, we are creating a greenhouse where overheating will be an issue. The third one is to remember thermal comfort is not only about temperature. We can create comfortable environments even at 27 degrees Celsius. And a very easy strategy is using ceiling fans, for example. And the last one, the most important thing that I would like to transmit you is that all these actions require time and long-term planning. We will face some heat events next summer, and you will remember this presentation. However, the easiest and the fastest response will be always to buy an air conditioner. So it's important to start addressing these issues in our homes as soon as possible. And of course, considering heating and cooling as a whole in the building design. We don't want to increase energy demand for heating in winter. I can tell you that following these steps, sustainable cooling is guaranteed. And this is the end of the presentation. Thank you very much.
Thank you very much for that. If anyone has any questions, can you please type them into the chat? Don't have any at the moment, but I'm sure people are absorbing what you've said. Do you think that in the UK we are making any moves towards what you're talking about? It seems to me that the focus is still on reducing energy costs for heating.
I mean, the major problem is the decarbonization of heating, and I agree that that is an important challenge. I think that the part O in the building code in the UK is a fantastic strategy. My concern is that this part O is only for new buildings. And most of the building stock is already there. And all the strategies that we are implementing right now are based on insulation and the electrification of heating. And probably what we are doing is that when we are increasing the overheating problem, we are installing a heat pump specifically for heating. And we are not considering that probably in the future we are going to have a huge demand for cooling. So I think that it's important to start considering what I said at the end, building and heating and cooling as a whole in the building design, and try to start planning our interventions properly for a changing climate.
Okay, we have a question come up. Do you have any views on the potential benefits of district cooling?
Yes, of course. I mean, district cooling is even district heating is a much more efficient way to 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 share and to minimize the total cooling capacity or heating capacity that we install. A more efficient way to generate and distribute heating and cooling. Probably a good opportunity in the UK is something that even in Oslo we were starting to explore is a fifth generation district heating and cooling system where we can have a network for heating and cooling. My concern here is that probably the heating demand will be much higher and it will be very difficult to control. But yes, of course, I mean.
And then there is another question. Some years ago, there was a trend to introduce chilled beams, which could be cooled overnight, particularly in commercial buildings. Is this less popular with the encouragement of ventilation and the personalization of comfort?
I don't know about what is chill beams. Sorry, is that
I think chilled beams are used. I'm aware that they're used in Hong Kong, so that they are essentially cooled panels in the ceiling of rooms to provide effectively the cooling within that room.
Mm-hmm.
But obviously they're not something that
Well, it's another strategy for heat dissipation, and of course, it's a strategy, my understanding, with very low energy consumption. It's a passive strategy that we can integrate also. So I think here, as I say, it's important to understand the heat flow in our buildings in winter and in summer, and try to make sure that if we have in the UK solar heat gains, that probably is one of the major problems in summer because we are not protected for that, how to dissipate these heat gains. And this is something that we can do by ventilation or probably by this technique.
Okay, there is a question: what is the cost implication of cooling? I'm not sure quite what that means. I mean, my feeling at the moment is that cooling systems are mainly installed in commercial buildings, not really in individual homes. There's not much in terms of air conditioning going into individual homes at the moment.
Yeah, I can. That is what I see, but I can also see how many residential buildings are starting to install air conditioners. It's something that we are starting to see here. And my view is that with high probability, we may not need cooling in the UK if we address these steps properly. Um, the major benefits that we can get in the UK are related to solar protection and heat dissipation, even by the integration of more thermal comfort variables, for example, using a high air speed. With these three key solutions, solar protection, heat dissipation by a better ventilation, and using more thermal comfort variables, for example, with ceiling fans, it can be very easy to create comfortable indoor environments without the need of air conditioning. The problem is that I understand this may require more time, more planning, probably more investment, even sometimes. So it may be less popular than just going and buy an air conditioner, something that you can start quickly in your home. This is something to balance and to think about. And it's also important to think that right now, probably we are electrifying heating with heat pumps. Probably in 5 years, we're going to buy another heat pump, in this case, only for cooling. And heat pumps can also be reversible. So with the strategy that we're following now, we maybe are duplicating the amount of systems that we are installing in our homes now.
Okay. A comment. The suggestion is that chilled beams are a bit like storage heaters, but as coolers. So it's effectively building up a reserve of of chillers that can be released during the day. And
I
I
see.
guess it
Okay,
links to the next question, which could you explain the nighttime cooling benefits? Because somebody didn't altogether follow what you were saying.
Nighttime cooling benefits related to cooling systems or passive cooling?
Uh, doesn't say. I am assuming that what you there are ways of because it's going to be colder during the night. Are there methods to retain to sort of cool things down and then allow that to mitigate the rise in temperature in the building during the day?
Yeah, exactly. Here is the use of the thermal mass, of the building thermal mass. I mean, there are two strategies that we can use to take benefit of the lower temperatures that we find at night. One is to use the thermal mass of our building to absorb the heat gains that we have during daytime, and then to release them at nighttime when we have a lower temperature. So at night, we cool down the thermal mass of the building. We try to keep the temperature low in our building structure in a way that during daytime, if the building can continue absorbing the heat gains without decreasing the indoor temperature. That's something very easy that we can address with proper ventilation. But in a similar way, if we have an air conditioner, this was the last part, the step 8. If we have an air conditioner and we integrate thermal energy storage, if we run the air conditioner instead of at daytime where we have 30 or 40 degrees Celsius outside, at nighttime where we maybe have 20, 25 degrees Celsius, the seasonal efficiency of the system will be much higher, and we are able to reduce the energy demand for cooling by close to 25%. If we combine this with a much lower electricity tariff at night, the economic savings can be huge.
Okay, thank you. Are there any more questions? Right, yes, one more. Is there any successful ventilation model or solution perhaps used elsewhere in the world that we can implement in the UK?
We have many solutions for ventilation. This is the diagram that I was explaining at the beginning. And ventilation can be driven by wind, by solar, or by the stack effect. But I can tell you the most effective strategy is cross ventilation. We don't need to install a fancy device to promote ventilation. You are able to open opposite windows in your house. That will be the easiest and the best strategy to dissipate heat.
Okay, there is a question, somebody who missed the first part of the talk, and therefore it may have been covered, but I don't think it actually was. What is the ratio of compressor type cooling to heating? I've always considered it to be 3-to-1. Is that still correct?
You mean the efficiency, you mean?
Well, I've read it out as it is written. I'm not altogether clear.
Yeah, I mean, the efficiency of the, for example, when we are going to buy a reversible heat pump for heating and cooling, here we used to call the coefficient of performance for heating and even for cooling the same. When we buy a reversible heat pump, we may check that we have two different indicators, the coefficient of performance and the energy efficiency ratio. Basically, it's the same indicator. We compare the thermal capacity with the energy input, with the power input that we need. And normally this value may range between 3 and 4. So it's quite similar for heating and cooling. I'm not sure if this is the question.
To heat or cool per degree temperature. Tim, it might be worth you coming on mic to clear this one up.
Yeah,
Okay. No. Are you on mic? I can't see whether he's on. Yeah, okay. Could you just explain the question? I think we're a little bit confused as to exactly what your question is. I'm not hearing you at all. I think we're going to have to leave that. Are there any other questions? Nothing else is popping up in the box. No. Okay. Right. I think we will bring things to a close. If questions occur to anyone afterwards, please email them to me and I will pass them on, and I'm sure we will Jesus will be happy to give us an answer to that. Yes, thank you for that. So we'll bring the talk to an end at this point. Thank you very much. It was a really interesting talk, I think quite thought-provoking. And it'd be interesting to see how things do develop. It's not something I'd really thought about as a serious issue for this country, but clearly there are things that we should be doing now that will help us for the future. So thank you very much. Yeah, seeing a lot of thank yous coming up in the comments.
Thank you, Brian, for the invitation. I am available to anyone that is interested in this topic. I am at Oxford. Thank you so much.
Okay.
Have a good evening.
Okay. I will end the okay.